Hi everyone, and welcome to my session, Durability with Agility. All you need to know about Couchbase durability. My name is Lior King, and I'm a Senior Instructor and Solutions Engineer at Couchbase. So what are we going to talk about? We'll explain what durability is and what it is used for. We'll discuss the durability modes that Couchbase offers in the former versions of Couchbase, before version 6.5. We'll discuss what changes were made to Couchbase 6.5 in terms of durability. We'll see how you can set the default durability mode for your buckets with Couchbase 6.6. We'll learn how to use the new durability modes in your code in various languages. And we'll talk about the performance impact of the new durability modes, how you can tune your system, and how you can get some metrics and statistics from Couchbase that are related to durability. So let's get started. We'll begin by explaining what durability actually is and why you should care about it. Couchbase is a memory-first system that offers persistence. Everything you do is done in memory first, and then it is persisted to disk, unless you are using an ephemeral bucket. If you set your bucket to have replicas, as you should, especially when it comes to production environments, then Couchbase replicates your change from the memory of the node that holds the active V bucket to the memory of another node that holds the replica, where it is also persisted to disk to the V bucket replica. Couchbase is tuned to give you incredible performance. By default, when a client is making a change, like adding a document, updating a document, or deleting a document, Couchbase will perform that change in the memory of the node that holds the active V bucket of the document. And then it sends an OK to the client. Then Couchbase replicates the document to another node asynchronously and saves the document to disk, again, asynchronously. The advantage of performing these operations asynchronously is obvious. The client doesn't need to wait for the document to be replicated or to be persisted to disk. Couchbase uses a queuing mechanism for the replication and for the persistence. The result is super speed. But what if something goes wrong? What if the client sends the document to the node and then it gets an OK, and just a fraction of a second later, the node crashes? The client thinks that the change has been committed, but in fact, the change is lost. That is because it existed in memory only, and Couchbase didn't manage to replicate the document to another node or to persist it to disk. So that brings us to durability. What is durability? It is the ability to keep stored data consistent and intact even through issues such as node failures, drive failures, or data corruption. Durability can have different levels. The level of durability will determine the level of protection against abnormal events. Durability is not availability. Availability refers to systems uptime and is achieved by redundancy or replication. Your system can be available and you still might end up losing data. Couchbase offered various durability modes in previous versions of Couchbase Server, before version 6.5. Let's see how they can be achieved. Couchbase 6.0 and older offered two dynamic durability settings for key value operations. These settings are optional parameters that can be added to individual key value operations. The settings are replicate to and persist to. Replicate to sets the number of nodes to replicate the data to. Persist to sets the number of nodes to persist the data to. By default, these settings were set to none. That means that the client doesn't need to wait for the change to be replicated to another node or to get persisted to disk. Replicate to is an enumerator, and it can be set to none or 1 or 2 or 3. If you set the replicate2 parameter to 1, that means that the client will wait for the change to be replicated to at least one node. If you set the replicate2 parameter to 2, that means that the client will wait for the change to be replicated to at least 2 nodes, and etc., etc. Persist2 is also an enumerator, and it can be set to none or active or 1 or 2 or 3. If you set the persist2 parameter to 1, that means that the client will wait for the change to be persisted to disk in at least one node. If you set the persist2 parameter to 2, that means that the client will wait for the change to be persisted to the disk in at least 2 nodes, and etc., etc. All Couchbase SDKs enable you to set these two parameters when you issue a key value operation. Here is an example in Java SDK 2.7. In this example, the client will wait until the document is both replicated to another node and gets persisted to disk. If one of these operations does not succeed, the client gets an error. The replicate2 and persist2 parameters are supported by the new set of SDKs that was released this year 2020, of course, and by the older SDKs as well. Here is an example of using replicate2 and persist2 parameters in Java SDK 2.7 and Java SDK 3.0 with an upsert command. Notice that in the new Java SDK, every key value command can get an options object, and the replicate2 and persist2 parameters are durability options that can be set as a part of the command options. Let's see another example using the .NET SDK with C#. You can see how you can use replicate2 and persist2 parameters in .NET SDK 2.7 and in .NET SDK 3.0. Notice the change in SDK 3.0 with using an options expression that holds all the options. This is one of the main differences between the old SDK that have used overloading extensively versus the new SDK, which uses a more modern, elegant, and dynamic approach. Here's an example using Python SDK 2.5 and 3.0. Notice the change in the new SDK 3.0 with the durability parameter that holds the durability options. The replicate2 and persist2 options are set in the client durability object. We will later see the new durability modes of Couchbase 6.5 or higher, which are considered server durability modes and not client durability modes, as you can see here. The last example is of Node.js SDK, and both SDKs 2.6 and 3.0 support the replicate2 and persist2 options. In the Couchbase versions before 6.5, the replication and persistence were always asynchronous. That means that there was no process that coordinated them, and they were simply managed by a replication queue and a persistence queue. The durability was handled by the client's SDK. The SDK uses an observe mechanism to check whether the document has been replicated and/or persisted. That observe mechanism performs periodic polling to check whether the document has been changed by comparing the document's revision, which is like a sequence number that is a part of the document's metadata. But that observe mechanism presented two main issues: a dirty reads issue and the lost writes issue. Let's explain what these issues are. Let's assume that the client issues an upset command. The changed document is sent to node 1, and the client gets an OK from that node. That change is now sent to the replication queue and to the persistence queue of that particular node, the node that holds the active vbucket. Now the client polls the replica node and checks if the revision of the document has been changed with a new revision. In this illustration, we've changed the revision from 1 to 2. The SDK checks and realizes that the revision is still the old revision. So it figures that the document didn't get replicated successfully to the second node yet. Now the SDK polls the replica node again and matches the revisions again. And now they match. So the client knows that the replication has succeeded, and the client can continue with the next statement. But that mechanism presents an issue called dirty reads. Let's examine that scenario. Application server 1 changes the document on node 1. Its sequence is changed from 1 to 2. The application gets an OK. Now comes a second application server and reads that same document. It will get the new revision of the document, right? But a fraction of a second later, node 1 crashes. The document has not managed to be replicated to the replica node yet. So application server 1 will get an error because it will wait for the document to be replicated, but since it will not get replicated, application 1 knows that the change did not succeed. Couchbase will initiate a failover process in which it will promote the replica to become active. But that replica holds the former version of the document. So in fact, application server 2 read a version of the document that should have never existed. That scenario is called a dirty read scenario. Another problem that Couchbase had in the pre-6.5 versions is the lost writes problem, and it occurred when the bucket was set for 2 or 3 replicas. Let's assume that the bucket has 2 replicas. Application server 1 changes a document and its sequence number is changed from 1 to 2. The application server gets an OK from the node 1. The document gets replicated to node 2. The application polls node 2 and gets an OK that the change was made. Now, node 1 needs to replicate the document to node 3, right? We've got 2 replicas. But then node 1 crashes before that happens. So now Couchbase initiates a failover process. But in the previous versions of Couchbase before 6.5, in case of a failover, Couchbase randomly selected the vBucket to promote. Since there are 2 replicas, Couchbase might decide to promote the replica on node 3 instead of the replica on node 2. So let's assume it is node 3 that gets selected. That will promote the older version of the document. And so if the application reads that document again, it will get the old version of the document. So in fact, we've lost the write that the application has initiated. If node 2 is promoted, the application will read the newer version of the document. Both issues of dirty reads and lost writes have been taken care of in Couchbase 6.5. Couchbase 6.5 comes with a new durability mechanism that solves the issues we've just discussed. Let's see what has changed. First of all, the responsibility of ensuring that a key value operation is durable has shifted from the client to the server. With the new mechanism, the client no longer uses an observe mechanism in which it checks whether the document has been replicated or persisted to disk. That responsibility has been shifted to the node holding the active bucket of the document. When a durable write takes place, Couchbase replicates the document to another node synchronously. That's right, synchronously. The client gets an acknowledgement from the node that holds the active vBucket when the document was safely replicated and or safely written to disk. To avoid dirty reads, Couchbase uses something we call prepared mutations. That is something like a snapshot of the document before it was changed. So if during a durable write process, another application reads the document, it will get the older version of the document, as long as the durable write is still in progress. Another improvement that was added to Couchbase 6.5 is fixing the lost writes issue. When a failover occurs and the bucket is set to 2 replicas or more, Couchbase checks every vBucket replica and promotes the most up-to-date replica. The new durability mechanism supports 4 durability levels: none, majority, majority and persist active, and persist to majority, which is the most durable level. Let's discuss each durability level and understand what it offers. We'll start with the default durability level, which is none. With this mode, the client sends the change to the node that holds the active vBucket and gets an acknowledgement right after the change was made in memory. Couchbase will asynchronously replicate the document to another node and persist the document to disk. This is the fastest mode, and again, it is the default mode. But, as you remember, that comes with some risk. The client sends the document to change, then it gets an OK. But if the node crashes right after the change, before the document has been replicated to another node or before it got persisted to disk, then the change is lost. So if we decide we need a higher level of durability, we might choose the majority level. With that level, the client sends the document to change to the node holding the active vBucket. That node will not send an acknowledgement to the client yet. It will replicate synchronously the data to another node, and then, when the replication has completed successfully, only then the client gets an OK that the change has completed successfully. Then the document will get persisted to disk asynchronously in both nodes. If there are 2 replicas, the majority mode refers to the majority of the replicas. So when there are 2 replicas, which means 3 copies of the document, then the majority is 2 copies. But the majority durability level is not perfect. Let's describe a scenario when the majority durability level might not be perfect. The application sends a change to node 1. The document gets replicated to node 2 synchronously. The application gets an acknowledgement from node 1. If node 1 crashes, we still have the replica on node 2, right? But if node 1 crashes and before Couchbase has initiated the failover, node 2 crashes as well, we've lost that document change. Even if these nodes are restarted successfully, the change is lost because it was not persisted to disk yet. Another scenario that might occur is that node 1 crashes and restarts before an automatic failover kicks in. Couchbase will read the document from the disk of node 1, but since the change did not persist to disk, the change is lost. That brings us to the next level of durability, which is majority and persist active. With this mode, the client sends the change to node 1, the node that holds the active vBucket. Node 1 replicates the document to node 2 and also persists the document to disk. Only when both operations are successful, then the client gets an OK from node 1. The document is also persisted to disk on node 2 asynchronously. The majority and persist active mode now protects the data on disk. If both nodes 1 and 2 crash, when node 1 recovers and it will need to read the document, it will get the change. But what if node 2 recovers and node 1 cannot recover? If node 2 recovers and you decide to hit the rebalance button, then the change is lost. Couchbase will promote the replica on node 2, and on its disk, there is an older version of the document. So we've lost the change. That brings us to the highest level of durability, which is persist to majority. With this level, the client sends the change to node 1, which holds the active vBucket of the document. Then node 1 synchronously replicates the document to node 2, and node 1 persists the document to disk, and node 2 persists the document to disk. And now, only after the whole saga has completed the replication and the persistence in both nodes, the client gets an OK that the change was committed successfully. Now, if both nodes crash, it doesn't matter which node recovers, the document is safe and sound on the disk of both nodes, and the change is not lost. Persist to majority is the most durable mode of Couchbase, but bear in mind that it is also the slowest mode. The client needs to wait for the whole process to finish, and that will impact the performance. During a durable change, there are other clients that are performing operations on the database. Let's assume there's a document in the database that application 1 wishes to change with durability. Let's assume it wants to change a field from A to B. Now, application 1 waits for an acknowledgement from the cluster. Couchbase retains the previous version of the document until the durable write completes successfully. In the meantime, application 2 tries to read the document. Since the durable write is still in progress, application A will get the previous snapshot of the document that holds the value A and not B. Application 3 comes along and wants to change the document, whether it is a durable change or an asynchronous change. It doesn't really matter. In either cases, it will get an error message. Application 3 can retry the operation later again. Now, application 1 gets an acknowledgement from the cluster that the write operation has completed successfully. The previous version of the document is no longer retained. So if application 2 reads the document again, it will get the value B and not A as before. That mechanism, alongside synchronous replication handled by the cluster, guarantees that dirty reads will not occur anymore. If you are using Couchbase 6.6, you can set a durability level for every bucket. When you create a bucket, you can specify a default durability level. The default setting is none. Once you change it to any other durability level, every key value operation on that bucket that doesn't have a specific durability setting will be a durable operation, and it will use the bucket's durability level. You can also change that setting on the fly if needed. Again, this is a new feature that was added in Couchbase 6.6. If you create an ephemeral bucket, you can set a durability level for it too. Although ephemeral buckets do not have any persistence to disk, you can still use the majority durability level if necessary, and you can set it as the default mode for your ephemeral bucket. So now that you know why the new durability modes are much better than the old ones, and you might want to use them, let's see how you can embed them in your code. To use the new durability modes, you need two things. You need Couchbase version 6.5 or higher, and you also need the new SDK 3.0. If you're using Golang, then you need SDK 2.0 or higher. The Scala SDK is a new SDK and already supports the new durability modes. The new SDKs still support the old durability modes, Replicate to and Persist to, and you can still use them, especially if you need to support Couchbase 5.5 or Couchbase 6.0. Here is an example in 4 languages for how to use the new durability modes. You'll notice that there is an enumerator that enables you to easily choose the right durability mode from a list of modes available. and that you can set the durability for every key value operation. Couchbase is a distributed database. Like in most distributed systems, there is a possibility that something will go wrong. For example, if there are network issues, if the node holding the replica doesn't respond, the active node might try to replicate to another node that holds another replica. If that fails too, there is uncertainty whether the replication succeeded or not. If the node holding the active vbucket fails to respond, there is still uncertainty whether the operation succeeded. These kind of scenarios might cause ambiguous results. So, if you get an ambiguous result, here's what you need to do. If you've attempted an idempotent operation such as an upset command, simply retry the operation. If you've attempted another kind of an operation, you need to verify the current state of the saved data, whether or not the change actually succeeded. Then reattempt the durable write. In case you still get ambiguous results after a few retries, you probably would need to return an error to the user. Durability isn't cheap, and it comes with a price. The higher durability you choose, the more impact it will have on your performance. There is a clear trade-off here that needs to be taken under consideration. You can tune your cluster to produce better performance when you perform durable operations using the majority and persist active level or persist to majority level. On the Couchbase web UI, you can choose Settings and then General. Under the Data Settings section, you'll notice the Writer Thread Settings title. This parameter determines the number of threads that Couchbase will use for performing disk I/O operations. You can change the setting from default to disk I/O optimized or to a fixed value. If you choose disk I/O optimized, Couchbase will perform its I/O operations with the same number of threads as the number of cores it has on the data service nodes. That is, if you have 16 cores, Couchbase will use 16 threads. You can also specify a fixed value of threads, up to 64 threads. Setting the writer threads to disk I/O optimized or increasing the number of threads has pros and cons. On the one hand, it allows for more vbuckets to be written in parallel, and that increases the I/O throughput. You might increase the throughput of your durable operations by dozens of percents and gain lower latency. However, disk I/O optimized will increase the CPU utilization, and it will cause more I/O load, and it will produce higher fragmentation. Note that this setting will impact the entire cluster and not just a specific bucket. So, changes to the default thread allocation should not be made to production systems without prior testing. If you'd like to monitor durable operations, you can use the cbstats utility that comes with Couchbase. You can use cbstats all command and search for all the statistics that contain the word sync_write. These are counters that Couchbase offers for monitoring durable operations activity. Notice there are 3 counters: accepted count, aborted count, and committed count. The accepted count is the number of commands that were accepted by the node that holds the active vbucket. The committed count is the number of commands that were committed successfully in the cluster. If there are no issues, the accepted count should be equal to the committed count. In case of issues, you'll see the aborted counter increases. That indicates that there might be problems with the cluster, a network problem, disks are too slow, CPU resources are not enough, or anything that can cause the durable write to get aborted. The statistics can be broken to every specific vbucket if you need. That will help you identify if the problem is concentrated in a specific node or in specific vbuckets. Simply add the vbucket-details option to the command and get the counter for each vbucket separately. CBstats can also help you get some performance statistics in the form of a histogram by adding the keyword timings. Couchbase will display stats for every durability level separately. From the output you can see here in the slide, you can notice that there were 1481 commands that have used the majority level. 164 commands have completed under 1342 microseconds, and they are 11.14% from the total amount of operations. Another 134 operations have completed between 1342 microseconds and 1470 microseconds. Together with the 164 commands from the former line, they are about 20% of the total operations, and so on and so on. At the end, you'll also notice the average time for all the commands together. Couchbase comes with a stress test tool that you might be familiar with. That is CBC-Pillow Fight. CBC Pillow Fight now enables you to set durability levels for your stress test. You can change the durability level and examine the performance impact that it has on your cluster. CBC Pillow Fight can be used for testing the older durability mechanisms as well. You can use the parameters --persist-2 and --replicate-2 to set the persist-to and replicate-to values for the test. Then you can run the test and measure the impact of these parameters. With that, we came to the end of this session. So what have we learned? We discussed the durability options of older Couchbase versions, pre-6.5. The durability was set using the parameters persist-to and replicate-to. The client's SDKs implemented an observe mechanism to check whether the changes were replicated to another node and/or persisted to disk. Couchbase 6.5 has an improved durability and consistency engine, which eliminates problems such as dirty reads and lost writes. This mechanism uses synchronous replication between nodes, and now the logic is handled by the cluster. Couchbase 6.5 offers 4 different durability levels: none, majority, majority and persist active, and persist to majority. We've also discussed the performance impact of using these modes. We've learned that with Couchbase 6.6, you can set a default durability level for each and every bucket. That level is selected in case you didn't use a specific durability level. That setting can also apply to ephemeral buckets. Using durability modes casts some performance impact. We've learned how you can change the number of writer threads to gain more I/O throughput, and how to get counters and metrics that can help you track issues. And we've also learned how to perform stress tests with different durability modes using CBC Pillow Fight. And that's it. My name is Lior King, and I hope you've enjoyed this session. If you have any questions, please submit them in the chat window, and I will be happy to answer them. Thank you.